The center of Earth is almost 6,400 kilometers beneath your feet. The deepest hole humans have ever drilled reached only about 12 kilometers. On the scale of the whole planet, that barely scratches the surface. Even so, scientists have identified a thin crust, a vast rocky mantle, a liquid outer core, and a solid inner core. Most of this picture came from studying how earthquake waves travel through Earth. When an earthquake breaks the surrounding rock, it releases energy in the form of seismic waves. Some waves travel along the surface, while others pass directly through the planet. As those waves move through Earth, the material inside changes their speed, direction, and strength. Seismometers can detect them when they return to the surface, even on the other side of the world. Scientists compare when each wave arrives, how strong it is, and which stations never receive it. You can think of this as learning about a hidden room by listening carefully to its echoes. Earthquakes produce two especially useful kinds of waves that pass through the planet. The first is called a P wave because it usually arrives first. A P wave repeatedly compresses and stretches material in the same direction that the wave is traveling. This type of motion allows P waves to pass through both solids and liquids. The second kind, called an S wave, moves material sideways as the wave travels forward. Liquids cannot support this sideways shearing motion, so S waves stop when they reach a liquid. Both kinds of waves change speed when the material's density, rigidity, temperature, composition, or physical state changes. A change in speed makes the wave bend, similar to the way light bends when it enters water. Part of the wave can also reflect from a boundary and travel back toward the surface. By measuring these bends and reflections, scientists can locate boundaries deep inside the planet. The first important clue about Earth's interior appeared before scientists could record earthquakes. Isaac Newton calculated that Earth's average density was roughly twice the density of common surface rocks. His results showed that much denser material had to exist somewhere inside the planet. Earthquake records later helped scientists work out where that dense material was located. In 1906, Richard Dixon Oldham compared seismic waves recorded after several large earthquakes. Waves reaching the far side of Earth behaved as though a large central region had interrupted their paths. Oldham's calculations provided the first strong seismic evidence that Earth has a core. A few years later, Croatian seismologist Andrija Muhorovičić studied an earthquake near Zagreb. Some of its waves reached nearby stations along the expected route through shallow rock. Other waves arrived sooner, even though they had followed a longer route through deeper material. They arrived first because seismic waves traveled much faster through the deeper material. Muhorovičić concluded that a sharp boundary separated the surface rocks from a different layer below. We now call this boundary the moho, and it separates the crust from the mantle. The crust is around 5 kilometers thick beneath some oceans and can exceed 70 kilometers beneath major mountain ranges. Beneath the crust, the mantle continues down to a depth of about 2,900 kilometers. The mantle is mostly solid rock, although it can deform and flow extremely slowly over geological time. As seismometers became more sensitive, the waves passing near the core revealed another strange pattern. Beyond a certain distance from an earthquake, seismometers stopped detecting direct S waves. P waves continued through the core, although they slowed sharply and bent enough to miss a large region of the surface. Scientists call these regions with missing direct waves seismic shadow zones. Since S waves cannot cross a liquid, their shadow zone showed that the outer core is liquid. The bending of P waves allowed Benno Gutenberg and other seismologists to place the core boundary about 2,900 kilometers below the surface. At that stage, scientists believed the entire core was liquid. Then, in 1929, a powerful earthquake struck near New Zealand. Danish seismologist Inge Lehmann carefully compared recordings of that earthquake from stations around the world. She found faint P waves inside a shadow zone where the existing model predicted almost no signal. Lehmann realized that another boundary inside the core could redirect some wave energy into that region. In 1936, she proposed that a solid inner core sits inside the liquid outer core. More sensitive instruments later detected the wave patterns predicted by her model. Seismic waves reveal Earth's structure and physical state clearly. While its exact chemistry requires additional evidence, scientists combine seismic records with gravity, Earth's magnetic field, surface rocks, meteorites, and high-pressure laboratory experiments. Together, this evidence indicates that the core is mostly iron, while the mantle consists mainly of dense silicate rock. Today, seismic tomography combines recordings from many earthquakes and thousands of stations around the world. Computers use small differences in wave speed to map cold sinking slabs, hotter mantle regions, and other structures deep inside Earth. Every large earthquake sends new measurements through places we cannot reach, and those measurements continue to improve our picture of the planet.